All right. Hello, everyone, from the campus of Carnegie Mellon University in Pittsburgh, PA. We welcome you to today's SCI webcast, Quantum Computing Meets High Performance Computing Skills in the Classroom. My name is Dan Justice. I am an AI and quantum computing researcher here at the Software Engineering Institute, and I would like to thank you for attending. We want to make our webcast day as interactive as possible, so submit questions in the YouTube chat area now, and we will get to as many of them as we can. Now, I would like to introduce my guest for today. As a senior technical marketing engineer at NVIDIA, Monica Van Dieren specializes in quantum and high-performance computing, driving the CUDA-Q academic initiative. Before joining NVIDIA, Monica contributed to IBM's Quantum Accelerator program. Welcome, Monica. Thanks for joining me today.
Hi, it's great to be here.
That's awesome. Now, as you are the star of today, I think everyone would like to hear a little bit more. Yes, come on, you are. We'd like to hear a little more about, how, like, a little bit of your background and how did you get into quantum? What was the happenstance that led you into this journey?
Sure. Yeah. So I actually received my PhD from Carnegie Mellon decades ago. So I'm a local here in Pittsburgh. And I was a math professor for over 20 years, and then happened to take a class in 2006, like a long time ago, in quantum computing, back in the days where quantum computers actually were just experimental in physics laboratories at universities and could only, handle, 2 or 3 qubits at most. And found the course very interesting, but not very practical at that time. And I happened to just put the book on the bookshelf and saved it, fortunately. So around 2020, I happened to pick it up off of the shelf and dust it off, and noticed that quantum computing was starting to make a play in industry, and kind of changed fields. Actually went back to college, took some courses to fill in the gaps between my mathematics background and quantum computing, and left academia in 2022, something like that, and joined IBM, and then came over here to NVIDIA. So that's a little bit about my career journey.
Yeah, and right when you moved to NVIDIA, that was when I actually met you, and we collaborated together. And really, very much on your end, you created a tutorial and then gave 2 lectures at my class, and that was, I believe, Divide and Conquer. That was your first tutorial, right?
Yeah, that was the first tutorial of the CUDA-Q Academic, which is our initiative at NVIDIA for quantum computing education. CUDA-Q is our software platform and hardware platform for quantum computing. And one of the features of CUDA-Q is that it was built with hybrid compute in mind from the very beginning. So GPUs and quantum processing units working side by side, and then also another feature of it is a distributed compute, right? Sending parts of a workflow to the GPU where that makes sense, and parts to the quantum processor where the quantum processor is going to be efficient at solving those parts of that problem, and doing it in a distributed manner. So the whole purpose of that Divide and Conquer tutorial was to illustrate the concept of circuit cutting, so students could see how the workflow and the sort of hybrid compute environment might be carried out.
Right. Circuit cutting is one of those potentially advantageous applications for quantum computing. And so that was one of the reasons. But you would agree with that, yes?
I don't know if it's the application, but it's the method in which you can maybe optimize and scale quantum computing. So a lot of the applications are circuits that are very large, and most of the quantum processors are going to be smaller. So you have to take that large circuit and somehow divide it into smaller parts to be run on those smaller quantum processors, and then stitch those results back together. So yeah, it would be one of the methods in which applications would be run.
Makes sense. And from that, you've gone and created many more tutorials, actually, is what you were telling me earlier, right? Because there's lots more gaps that you have to fill for this space.
Definitely.
Yeah. And so I guess that's what you're here to talk to us about today, is the difficulties of merging and the challenges of teaching quantum computing and the need for HPC education within the space also. So I'll get out of the way, and you would like to take it from here.
Sure. Yeah, happy to do that. So I guess as the slide here indicates, I'll be talking about quantum computing education and actually the need for teaching high performance computing skills side by side quantum computing skills and like why that's important and how it might be able to get done. But before I jump into that presentation, though, I do want to make this as interactive as possible instead of just having me talking on the screen the entire time. I'd like to maybe find out a little bit about the audience. So if you are in the audience right now and have a browser window open or your cell phone handy, you can take an image of this QR code and go over to the Mentimeter site, answer a few questions, and I will then be able to hopefully address some of your interests and also target the presentation to your backgrounds as well. So I'm going to jump over here to the poll results as they start coming in so we can see who the audience is, because I've given you a little bit about background about me. I kind of want to learn about you. So I'm going to stop sharing this now. And it doesn't look like anybody is answering the poll yet, or it's not coming through. So I might just have to be doing this without that insight. But if you happen to be in that QR code and Mentimeter, as I continue on the presentation here in a little bit, make sure to fill in these questions so that we can make sure we're addressing your interest here. And all right, great. So we're interested in quantum computing and potential connections to cryptography and quantum education. Excellent. These are definitely two things we'll be covering today. And it'll be also helpful for me to know, in particular, your background on quantum computing. But if I don't get any results, then I'll just I'll start from the least common denominator, and we'll go from there.
Monica, if I can put in a small plug here, on October 14th, I'll be having another webinar with a colleague on post-quantum cryptography. So if anyone wants to join us that day, we'll be having another webinar then.
Okay, so I guess I'll go ahead and get started. I will talk a little bit about quantum computing and give an overview for those of you in the audience that might be new to the field. And then I'll introduce the concept of an accelerated quantum supercomputer and talk about the role of AI in developing and actually deploying this accelerated quantum supercomputer and how we would train our workforce for this. We'll finish off also too with some resources for you to learn more. So what is a quantum computer? I'll try to give a quick 1-minute introduction. I mean, this field is very technical, and you could spend years on trying to understand it, but we'll give you a 1 or 2 minute introduction to quantum computing by breaking it down by first comparing it to classical computing, where a classical computer uses bits to store and manipulate information to do the computations, right? They're basically tiny switches that are a 0 or a 1, on or off. You can think of that as an arrow pointing up or down. That'll be useful in our analogy here in a minute. When we look at quantum computers, so quantum computers use, instead of bits to store information, they represent information as qubits. Now, a qubit can be 0 and a 1, an up or a down, but it also can be both a 0 and 1 at the same time. So this is a property called superposition. Instead of the arrow pointing up or down, you can think about that arrow pointing in any direction, and maybe even thinking of it sitting within like a balloon. So there's a big catch with superposition. You think that, oh, wow, you have all these infinite ways of representing information because you can point that arrow in any direction. The catch is that with a classical bit, you can always peek into the computation and see if you've got an arrow pointing up or down, a 0 or a 1, and it's predictable. But for quantum and superposition, you can't look at the quantum state without, or you can't know what the quantum state is without looking at it. And so what that means is that we're going to be measuring it. So and with measurement, something strange happens. So you can think about that arrow sitting within a balloon, but imagine that balloon is opaque. You can't see inside of it. In order to measure it, you actually have to pop the balloon. And when you pop that balloon, the qubit's either forced to pick a side. It's going to collapse up or down to 0 or 1. Of course, this is all metaphorical. This isn't actually physically how a qubit works, but it's a way to think about it abstractly. And so for a state in superposition, if you run the computation again and again and again. So you have these arrows and it's pointing in the same direction and it's inside this balloon, but we can't see it. And we pop the balloon. We're going to get maybe different answers each time we pop the balloon. Maybe 50% of the time we get a 0 and 50% of the time we get a 1. That's essentially the way to think about a quantum computation. There are more things going on with quantum computation like entanglement and interference. I don't have time to get into that right now. We do have some resources available on Q2Q Academic to get into that. But for now, if you're new to quantum computing, I hope this is at least a understanding of how qubits maybe differ from bits in computation.
This is a really difficult concept to always convey to newcomers to quantum computing, simply because this isn't something that happens in everyday life. This isn't something that we can experience, and you'd have to be down at the quantum mechanical level to be able to experience this. And even our language isn't really set up to be able to convey this concept. And so the nuances that you're bringing into this, Monica, it's great, but it's hard to wrap your head around. It generally takes several classes to get students really familiar with this.
Exactly. But just like with computation, we don't have to understand how a computer works to be able to use a computer. And the same thing is with quantum computing, right? We don't need to understand bits and qubits to actually run a computer or a quantum computer. And so I want to talk a little bit about the differences between a classical computer, the actual physical device, and quantum computers. Classical computers realize their bits. The physical reality of these bits are with transistors. They're inside your phones and your laptops, and we don't have to think about them in order to use those computers. But they all use transistors. Something is different with quantum. Right now, we're in the early days of quantum, and there's a race to find the best way to build a quantum computer or to build a qubit. And right now, there are several competing technologies: trapped ion, superconducting transmon qubits, or maybe something entirely different. And we're not sure the winner of this race. In fact, the future might be a mix match of different types of quantum computing modalities, some that we might use for one sort of jobs, and other jobs we might use a different type of quantum device. So we're really at the early stages of the quantum computing era in terms of building the quantum computers. And so we have this unique way of representing information with quantum computing and all these different quantum computing modalities out there that we might actually be able to build a quantum computer with. But why are we doing this? And the reason is that the unique capability of quantum computation qubits to hold information and process information, that unlocks actually a whole new era of computational science that allows quantum and classical processors to tackle problems that we currently struggle with today, where the classical and the quantum are each sort of leveraging their own strengths. So for decades, actually, we've made incredible progress with classical computers, especially with GPU acceleration, for scientific discovery in all sorts of areas. But there actually are some fundamental questions that even the most powerful supercomputers today struggle to answer. Just take chemistry, for example. Designing new drugs, more efficient fertilizers, or even better EV batteries. These all come down to understanding how molecules behave. And a quantum computer could help simulate this with an accuracy that's impossible today, drastically speeding up innovation in these areas. But also in fields like logistics or finance, finding the best answer to complex optimization problems is a massive challenge. And quantum computing offers a new way that might be more efficient to find these solutions. And the point is, though, to think of it less as a replacement for classical computers and more as a powerful co-processor in a toolkit of accelerating computing. And so the future of computation is going to be quantum machines working in tandem with classical ones to solve problems that currently are out of reach.
If I could add something there, the one thing that is interesting about these applications is that quantum computers tend not to be good at really simple mathematics. So just addition and subtraction, there's no real advantage. They really are already looking at these more complicated problems, which are already having intense computational loads. And so that's why it's a perfect meld, and why students have to understand the high performance compute of what's already being used so that they can then bring in the quantum when it's needed?
Well, definitely, because high performance compute, I mean, it's struggling with some of these problems, but given that it's our only tool in the box right now, we're still making great strides and getting close to solutions with high performance compute. So knowing the limitations of high performance compute is definitely important.
Yeah, and that's where you're doing right here. Is you're bringing in the new toolbox. You're bringing in the screwdriver, not just the hammer.
Yeah, we have to use all of them. So let's teach them all. Exactly. So yeah, but I've talked a little bit about quantum computing and its potential applications, but the current state of the technology is not in full force, right? We have great quantum processors out there today. Industry is making great strides on this, but the current processors can only perform hundreds of operations on a limited number of qubits before the qubits are overwhelmed by noise and the computation is corrupted. So this means that the partnership that we've been describing between quantum and classical computers, them being both tools in the same toolbox, it's not just for scientific breakthroughs, but we actually need the classical and the quantum computers to be working together in order for just the quantum computer to function reliably. So in order for quantum computers to be useful, we need to solve the noise problem. And we can do that with error correction. We actually do this already with classical compute. We just don't have to think about it because the error correction is just so good and the noise levels of transistors are just so great, are so low in our regular computers that we don't think about this. But if you think about what happens when you scan a QR code at a restaurant and there happens to be like a ketchup smudge on it, you can still bring up the menu at the restaurant. And that's because you have error correction going on inside of your phone as you're reading off that QR code. It ignores in some sense or adjusts for that ketchup smudge. So in some sense, we're going to need to do that on a much larger scale in terms of the number of qubits and the number of mistakes and noise, and also on a smaller scale in terms of the qubits being very small and controlling them. It's not a macro object like a ketchup smudge. So the way for error correction to work is that you have a classical computer working hand in hand with a quantum computer, and the classical computer is constantly monitoring for errors and correcting them in real time. And so in order for this to work, you actually need to have a platform in which a quantum and classical computer aren't just connected, but they're connected very tightly with a low latency connection. And so that brings us actually to NVIDIA's vision of an accelerated quantum supercomputer. And as I've kind of mentioned multiple times, the real quantum computers now in the future aren't going to be standing in isolation. They're going to look like this, where there's a quantum device kind of represented here abstractly with this little atom sign next to GPUs and CPUs in a supercomputing center. And they need to, because we need those classical computers to carry out things like error correction and real-time calibration and control, and also hybrid algorithms. And right now we know that there are several competing qubit modalities: trapped ions, neutral atoms, photonics, superconducting transmon qubits. And as I mentioned before, we don't know which one's going to pull ahead of the others. And it could be that some of these qubits are going to be useful for some tasks and others for solving other problems. So we need to create a platform where we're not locking into one qubit technology today, but have a qubit agnostic platform where we can swap in and out different quantum modalities in a distributed manner. And we need to be able to orchestrate that. And this is done with Q2Q, our quantum computing platform. And so I did mention being qubit agnostic, and whoops. And what I mean by that is that we can just work with all sorts of quantum computing technologies and those companies building those technologies. So this is just a snapshot of some of the quantum computing companies that we're working with, that we're connecting our GPUs to their quantum hardware and experimenting on error correction strategies and hybrid compute. And many of these actual quantum computing company hardware can be accessible through AWS Bracket. And so while we're working towards this vision of an accelerated quantum supercomputer with all these companies and many more, we're actually a ways off from a fault-tolerant, useful quantum computing. But there's actually a clear path to get to there from the noisy experimental qubits of today. And we're going to have to overcome several roadblocks. And AI supercomputing is actually going to be the tool that allow us and researchers and engineers to remove these roadblocks in a number of areas. And so, and we're seeing progress in these areas as well. The quantum workforce is tackling this big list of challenges. And for instance, we need better, lower noise quantum hardware. So we have to design better qubits. And even if the quantum processors that we have today get less noisy, there's still going to be errors. They're never going to go away completely. So we have to have smarter error correction strategies. And we also have to have more resilient hybrid algorithms that are less sensitive to noise. And being able to execute these algorithms efficiently and the error correction efficiently is going to require a high-speed interconnect between the GPUs and the quantum processors. And so in order to overcome all of these challenges, we need AI supercomputing. And AI, of course, needs a lot of data to train it. And so the data in this case is going to be quantum computations data on noisy processors. So we need to be able to generate a whole bunch of quantum data as well. And we can actually use GPUs to do that generation of data. So these are the types of challenges that we're facing as an industry, and as an educational community, it's actually our responsibility to ensure the next generation isn't just aware of these problems, but actually is fully prepared to solve them. So effective training has got to be built around these challenges. And what I'd like to do for kind of the rest of this presentation is to explore in detail each one of these challenges, some progress we're making as an industry to overcoming them, and how our curriculum is structured to provide the essential preparation to the students who are going to be helping with these challenges as well. So let's start with quantum algorithms. They're often taught through textbook examples, but today's researchers aren't just programming those textbook algorithms into the computers. What they're doing is they're leveraging AI to discover more effective algorithms and ways to optimize the existing ones across many dimensions, such as reducing the qubit requirements so that they can run on small machines, enhancing the noise resilience so that they're less susceptible to noise. And as I mentioned, when we're running a quantum process, we have to do the measurement, typically at the end of the computation, to read out the quantum state. And those, we have to take many measurements each time we run that computation, because each time we run the computation, we might get a different result. And we're really looking at the probability distribution of those results. So if we can minimize the number of shots needed, that reduces the amount of computation that we have to have that quantum computer running. And so those are all areas in which we are taking these sort of textbook examples and even current new problems or new algorithms and trying to kind of extend what they can be carried out on today's devices and the ones of the future. And so one example of this where AI is coming into play is on the variational quantum eigensolver. This is a algorithm that's used for simulating molecules, one of the major application areas of quantum computing that I mentioned earlier. Traditional variational quantum eigensolver algorithm has limitations. It requires a lot of parameters need to be optimized. You can kind of think about this as thinking about a landscape and trying to find the minimum point in the landscape, the lowest point. If your landscape is very flat and maybe has one big dip, you might get stuck on this flat area and never find your way over to the low point. And so those are called barren plateaus. It's a big problem with quantum algorithms that variational quantum eigensolver suffers from. And so researchers are trying to come up with variations on that maybe are less susceptible to the barren plateau problem. And one of those approaches is with the generative quantum eigensolver. And this acts like a large language model. So instead of generating a sentence from one word at a time, like a large language model would, we generate a quantum circuit, sort of one block of gate operations at a time. And the idea is that we might be able to generate a circuit that's less susceptible to noise and converges to solutions faster than the traditional VQE might. And so to address this kind of area or this challenge in developing useful quantum computing, the academic modules that we've created provide direct hands-on experience that guides students through the entire process of writing their first algorithm, but also building and optimizing better hybrid quantum classical algorithms to bring those applications to life. So we begin with the fundamentals and quickly advance actually to research level applications, learning to write the code that fully leverages the powers of both the quantum and the classical computers of today and the future. And so we have some examples in finance and in chemistry that do this. The next challenge, go ahead.
Well, just to clarify, are you ever going to have just a quantum algorithm that's going to solve these problems?
So you can't run a quantum computer without a classical computer. So in some way, there has to be a classical component of it. That classical component might just be the error correction side of things, but that's going to be, inherent in the in that implementation. There are some quantum only algorithms, but they do require pre-processing and post-processing that are done on the classical device. I mean, how you get the quantum computer to do what it's going to do is through controlling it with a classical computer. So it's sort of like the question is like, there could be some algorithms that are like highly quantum, but there's always going to be some classical component to it, right?
Yeah, it was a trap question, right? But that's a misconception that I have a lot of students come in, and it took me several classes to realize I need to state this explicitly. So no, that's exactly I wanted.
That's a good point. Actually, quantum computing education, overcoming and misconceptions is a huge part of the educational challenge.
Mm-hmm. Yeah, there's a lot of zeitgeist out there.
Yep. Which changes daily.
Yes, it does.
Yeah, it's a fast-changing field. We'll get to that later and how education needs to address that as well. So another area in which researchers are working is building better quantum devices, less noisy qubits. So even if we've got better quantum algorithms, we're still going to need to build qubits that are less noisy and also can scale, larger quantum computers that have more and more qubits. So in order to build better quantum processors, though, first we need to understand the noise. And to understand the noise, we need to simulate the actual physical qubits, how they interact with each other. And some of these interactions actually come from our quantum program. It's entanglement. We want the qubits to interact with each other, but sometimes the device has quantum qubits interacting with each other that we're not programmed to. That's where the noise comes from. It's one of the areas in where the noise comes from. The noise can also come from the environment. And so these are the sources of noise we have to understand in order to design a better computer. And in order to design a better quantum computer, we have to do simulations of those quantum devices before actually, building it physically. And those are computationally expensive. And to understand the physics behind all of that, we did do a lot of calculations, and our Q2Q Academic Dynamics 101 series of modules actually introduces students to Q2Q Dynamics, which is our one-line API that allows students to carry out GPU-accelerated calculations necessary to understand quantum systems, studying things like Schrodinger's equation and Lindblad master equations, doing their time evolution. Students can get kind of hands-on with that with our Q2Q Dynamics tutorials. And then there's problems of data generation and quantum error correction that we're trying to solve. And they're the biggest challenges actually that we face today in some sense. And because even if we build better devices that are less noisy, there's still going to be noise. We still have to account for that in real time. And so we need better error correcting strategies. Current error correcting strategies aren't ideal. They often require many physical qubits to encode one logical qubit. So a machine that has 100 physical qubits, they actually might only be able to run algorithms that are on 10 error-corrected logical qubits. So this makes scaling quantum computers to thousands or even millions of logical error-corrected qubits even more challenging. So we're using AI to generate better error-correcting codes that might be more efficient in terms of the number of qubits required for the code. But it's not just the number of qubits that we have to pay attention to. Speed is also critical. If your classical device that's monitoring the quantum processor to detect errors takes a long time to decode that information, to identify what instruction set needs to be sent back to the quantum processor to fix the error. It needs to be done before the next set of instructions is carried out and that error propagates on the quantum computer. And so researchers right now are trying to are using AI to find faster ways of identifying the corrective instructions once the errors have been identified. That's called decoding. And these AI models, though, they require massive amounts of training data, which in this case means looking at data of noisy quantum computations. Now, we don't have enough quantum computers in the world to generate the trillions of data points that we need to actually train the AI models, but we can actually synthetically generate that data on our GPUs, and that's one of the things that we're doing, and we're actually teaching students about this too. So we have a quantum error correcting 101 series that takes students from the basics of error correction to learning how to apply the AI decoder in their strategies, as well as to address the need for the immense amount of data needed to simulate complex quantum systems. For AI models, the University of Copenhagen and the Technical University of Denmark actually are developing a semester-long course on large-scale simulation of quantum systems using Q2Q. So whether it be qubit calibration and control or effective error correction or simply running a large quantum circuit distributed over several smaller processors, we need low latency interconnect between the GPUs and quantum processors, and that presents a whole bunch of other physical challenges. But I want to focus on the distributed aspect of it here. And so what I mean by distributed is if you have a large quantum circuit, but you have several devices, we need to distribute that workload among those quantum devices, but we also might have part of the workflow that we have to distribute over all of our GPUs and CPUs as well. So many of the potential applications of quantum computing require thousands or millions of qubits. But most quantum hardware companies aren't designing one large quantum computer, but rather they're working on networking smaller ones together like this. So we need to be able to break a large problem down into smaller problems. So I've kind of represented that here with the graph, that being our kind of large problem that we want to break down into smaller problems and run those smaller problems on devices. So the smaller problems are highlighted in darker edges here in the graphs as this video will go on. And we can see that if we can break a big problem down into small problems, and if we can run those small problems in parallel with each other, we can get to a solution much faster than if we ran those small problems one after another in sequence. I mean, that's just one of the power of parallelization. So introducing students to concepts of parallelization and how to break a big problem down into smaller ones and how to distribute that in an efficient manner. That's the content of the Divide and Conquer Max Cut series of notebooks, Dan, that you mentioned at the very beginning of this webinar. And it turns out that this idea of breaking a big problem down into small problems, that's computationally difficult. And so what researchers are doing right now is to take a large quantum circuit and using AI to find an efficient way of breaking that down into smaller subcircuits, some of those that might be run on quantum processors, some of them that might be simulated on GPUs or CPUs. And then, of course, taking those results, another difficult problem is taking those results and stitching them back together into a solution to the original problem. And you want to do this so that there are many things that we want to optimize for. One might be the load on the quantum processors. Another might be minimizing the amount of post-processing that we do and the amount of information that we might lose along the way when we're doing this process of circuit knitting and circuit cutting. And so that's what the Divide and Conquer for Max Cut. So that's what the Divide and Conquer for Max Cut module does. It takes students from the textbook example of QA/OA for Max Cut, and then they learn to experiment with parallelization and circuit cutting. And these are both the key components of the adaptive circuit knitting where AI is applied to it in this research paper here. So we're taking students from textbook examples to current cutting edge research so that they can see how what they're learning in the classroom is actually being applied today, and they'll have the skills to enter the workforce and participate on those projects. So You may have noticed that we're not working alone on any of this. These are just the many of the collaborations that we have working with on applying AI to quantum computing challenges. And we're partnering with nearly everyone to advance the technology, from academics to startups to large corporations. We're working not just on improving the software, but we're looking at improving the hardware and looking at better applications. And all of these, though, the common thread is that we're using GPUs and AI supercomputing. And we're doing it not just for the simulation of the quantum algorithms themselves, but it's actually an integral tool in advancing AI, the vision of this accelerated quantum supercomputer. So,
Monica, if I could jump in, we just got two questions. And so I wanted to redirect. This is a perfect slide for that. Our first question is SEI developing their own quantum computer? And we're not a hardware shop. We are a software shop. And so no, we have yet to develop our own qubits. If you look over on the left, the quantum hardware builders, that's where just about most of the quantum computers right now are being built, right? So you can look at those entities and that will give you those. And then what is the lifespan of a qubit before decoherence? I think it depends on the qubit type. I think it's around 250 microseconds on average, give or take. I have to look into that a bit more. And with error correction, I believe we have broken the 1 second mark the other year. So,
it really depends on the technology, right? Every one of them is going to have different threats of noise and time. Yep.
Yeah, and the answer in the end is, at the moment, not drastically long, and certainly not as long as your classical hardware. But okay, please, Monica, continue.
Oh, no problem. So in addition to working on the research, we actually teamed up with several universities to develop curriculum, educational materials to prepare the next generation of quantum computing professionals. And so building this new curriculum is actually a major undertaking, and which is great that we have all of these partners helping us out. But the good thing is, too, we don't have to start from scratch. We can learn from the work in a related field, high-performance computing education. So a few years ago, the Innovation and Technology and Computer Science Education Working Group, I'm not going to say that again, it's a mouthful, but there's an archive paper here you can check out. They identified and grouped together 4 major challenges in high-performance computing education. And the first is how to teach, because we aim to prepare students for the future of quantum computing, and the future of quantum computing is hybrid. It's actually important that we're providing students with a practical experience in this hybrid compute environment using both GPUs and quantum processing QPUs, and dealing with things like scalability and distributed computing. So similar to high-performance computing education, we face a shortage of faculty trained in quantum computing, especially when one looks outside of the traditional fields of physics and computer science. And because our workforce is going to be made up of students from all across the disciplines, we need to make sure that we're getting the quantum computing education into all those STEM courses. So it's critical to create partnerships between industry and academia to develop and share up-to-date resources. Similar to high-performance compute education, problems are often requiring domain expertise. So we need to think about expanding the curriculum outside of those traditional physics and computer science courses to integrate it across the STEM curriculum. And one idea here is to take note of what's happened in computer science in the last 30 years. It's now taught in almost all STEM majors, and so similarly, we can think about starting to integrate quantum computing examples and concepts into non-quantum computing courses. And finally, when we think about designing curriculum, there are 2 common approaches. One is to identify learning objectives, and the other is a competency-based approach, where we design tasks that are often written as projects within a work context to prepare, the students for the workforce. And these tasks actually target knowledge, skills, and dispositions that lead to success in the workplace. So In particular, you can think about taking a textbook example of an algorithm and teach students how to push the boundaries of what can be computed on today's devices with that algorithm as like one approach to this. But I go into look at a particular example of how we might craft a competency for high performance computing and quantum computing. And that is to not only teach the quantum computing knowledge, such as entanglement and what a quantum ansatz is, but also bring into the lesson models of data management and performance monitoring tools so that students can examine accuracy, speed, and scalability of their algorithms. These are concepts of high performance compute that are not traditionally emphasized in a quantum computing course. And some of and then additionally, an effective curriculum needs to not only align directly with the current industry needs, equipping the students with practical skills like implementing and optimizing hybrid algorithms, which often will require an AI component, but also fostering the vital dispositions like adaptability and willingness to experiment that are the essential mindsets for working in a rapidly changing field. So one of the last poll questions I have actually is, to get your thoughts on this idea of developing and fostering those dispositions in the students that will lead them to success for working in the quantum workforce. It's not all about the knowledge and the skills, but also those dispositions. What do you think are those mindsets that we need to be fostering? And I'll go stop share for a second to go to the poll results to see what you all think.
And also, just to add a little bit at the end, one of the things that I've noticed is with before Monica came in and started working with us, one of the problems that we had with students is that we were very limited with the size of quantum computations and simulations that we could actually run. Right. And so if you aren't teaching students high performance compute at the same time you're teaching them quantum compute, you're going to actually reduce their ability to learn and their ability to experiment and iterate and get more experience with not just quantum computers, but even just reasonably sized quantum compute. And when I say we're limited, I think the largest experiment I'd ever have anyone run on their simulators, or which is generally on their laptops, was about 16 qubits. I once gave a homework assignment that was 22 qubits, and I had to redesign it because two students couldn't run it. And so you can imagine what you can do with 22 bits is not a lot, and what you can do with 22 qubits is slightly more. But all right.
Well, you bring up a good point that, and also some of the responses coming in about the dispositions of creativity. If we think about what defines creativity, one of the definitions out there, is I'm taking ideas from different areas and being able to like combine them together. So if we're teaching, and this is actually a challenge that like I saw in mathematics education, going all the way back to the beginning of my first part of this presentation of my background as a mathematics professor. Years went by in mathematics education where physics concepts were taught in calculus textbooks very minimally. And students had trouble translating what they learned in calculus to their physics classroom. And what happened with a revolution in the way that calculus was taught is you started to bring more of these applications into the calculus classrooms where students could see them side by side. So to encourage them to bring these disparate ideas or these ideas that are connected together to solve a problem, we actually have to foster that creativity and show them how we can put ideas together from different disciplines. And so this is like a key to fostering creativity, is to put students in an environment where those ideas are in the same place where they can bring them together to solve a problem.
Yeah, and going back to something that you've been talking about for a while, Monica, was is bringing in different cross-disciplinaries or different parts of the classrooms or topics. And something that happened to me recently, which was brand new, is that someone from the math department actually approached me and said, "Hey, we're interested about quantum computing." Right. And 5 years ago, it was hard to get the computer science department interested in quantum computing because that was considered a physics domain. And then and the computer science part and the programming part was considered some sort of intersection of like physics and science and computer science and maybe even material science at the time. And now it's a computer science topic. And now it's starting to be the mathematicians are interested in it. And so there is starting to be this kind of ecosystem where it's growing out of what it used to be.
Exactly. I mean, we need to be kind of preparing for that by building like the educational materials to be integrated and can be like in a modular format that can be pulled into different classrooms by different professors of different majors. And kind of importantly, we need to make sure that those modules focus on the skills that are being used today and in the future of the workforce, and that's hybrid distributed workflows. Having hands-on experience with GPUs and quantum processing units when possible, and taking this idea that the ACM, this is how they have laid out their curriculum standards as a competency-based approach, where you equip students not just with the knowledge, but also the skills and dispositions that they're going to be needing in the workforce. And so, I think that was a good way to sum it up. These are some of the resources in case you want to learn more about CUDA-Q, our platform for distributed computing. It's open source. It's actually a great way to get hands-on experiences contributing to GitHub, and great line on your resume when you're looking for jobs to get into the workforce. CUDA-Q Academic, if you want to learn more about quantum computing and try out some of our online modules to learn about error correction or applications of quantum computing, or just get started with the definition of a qubit. That material is available for you for free online to use. So I'll leave that slide up.
I got one more question, Monica.
Yep.
It reads, what skills do most quantum students lack, and what could they build towards?
Well, I think that we're seeing the students that are getting quantum computing skills right now are typically getting them from kind of a traditional quantum computing course and traditional maybe physics major, and so the skills that might be lacking there are the ones in high performance compute and AI. And the nice thing about adding on skills in high performance compute and AI is that they're transferable, because almost any scientific compute is going to need those.
Yeah, I mean, from my perspective, I do teach quantum computing more from a computer science perspective, or almost a coding perspective. And the funny thing is that programming seems to be one of the skills that students are starting to lack. It turns out that LLMs are doing a lot of the brunt, and so I do a lot of actual lab work and programming, and I have definitely noticed that students are starting to struggle more and more with writing the code by hand. Which, maybe that's just, I don't know. My teacher used to always say we would never have calculators in our pockets, and now I do. So, maybe that's just goes to show how archaic my my educational style is. But I think that's going to come back around. Anyways, I think that was the last question.
Excellent.
So, Monica, it was a great discussion today. Thank you for sharing your expertise. And thank you all for attending today. Upon exiting, please hit the like button below the video window and share the archive if you found value. Also, you can subscribe to SEI YouTube channel by clicking the SEI seal in the lower right corner of the video window. Our next webcast will be October 1st, and the topic will be using LLMs to evaluate code. We will also have another webcast on October 14th on post-quantum cryptography. Registration information is on the SCI website now and will be emailed out as well. Any questions from today's events, please send to info@sei.cmu.edu. Thank you all.